Good morning, everybody. Welcome to PMC pre-training online session. Today we're gonna talk about the VGO block, and we're gonna start today only focusing on the VGO hydrotreater. Then, we're gonna follow after the VGO hydrotreater. We move to the FCC unit and then the PNU. So thanks for attending, and I'm gonna hand over the presentation to Pilar, and as usual we're gonna pause after each explained slide in case something ambiguous that you need to clarify further. Thank you so much. Pilar, you can start now. Thanks.
Yes, thank you, Ahmed. Welcome to this online session. So today we are going to see the part A of this vacuum gas oil processing. But first, I would like to share a safety moment with you. Remember that in other sessions we have talked about temperatures, runaways in the reactors. So in these slides, we will show the main concepts of this temperature runaway and the possible causes of this runaway. So the raw materials, as you know, well, in a reaction react together during the manufacture of a chemical to give the product, or during our refinery processes. We have a lot of chemical reactions. Such a chemical process often releases energy in form of heat, and the reaction is described as exothermic. Remember this, the exothermic, the heat goes to the surrounding, the endothermic, the needs heat to proceed the reaction. A reaction may be exothermic even if you have to heat the reaction mass initially to get the reaction started.
Pilar, the voice is a bit interrupts most of the time, so I don't know whether it's the mic or whether it's the net. It keeps breaking up, kind of. So just
let's try again now.
Now is better, yeah.
Okay. So here you see the definition. As you know, the exothermic is one that loses heat, and the exothermic is one that gains heat from the surroundings. Okay. An exothermic reaction can lead to thermal runaway, which begins when the heat produced by the reaction exceeds the heat removed. The surplus heat rises the temperature of the reaction mass, which causes the rate of reaction to increase. This in turn accelerates the rate of heat production. As you know, the rate of reactions get faster if you increase the temperature. So that is the phenomena that is explained here. If you cannot remove the heat produced by the reaction, you will increase the reaction rate. So during the temperature runaway, highly exothermic cracking reactions can take place. These temperatures can rise rapidly to well above the equipment design temperature. Okay, that's why it's so important to control these temperatures in the reactor. Okay, because you can go up to the design temperature of the vessels that contains the catalyst, so it can create a serious damage of the reactor and a safety, of course, concern. So what can cause this temperature runaway? You are working at normal temperature, and then you start to increase the temperature suddenly. So it can be produced by a reduction in space velocity over the catalyst. Then you will have a lot of residence time, and they can produce this temperature runaway. You can have a problem removing the heat of the reaction from the catalyst. For example, in the reactors we have the quenches. If you lose one of the quench, you can have the temperature run away. Or if you have during the startup, during normal condition, the overheating because of the abnormal operating procedure, you can also have this temperature run away. The temperature run away is a very serious situation that requires immediate attention. Okay. How can we stop the runaway? To keep a temperature runaway, you need hydrocarbons and heat. So if you uh, eliminate one of these, you will stop the temperature runaway. In this case, you have, as I tell here, no? Therefore, removing one or the other will cause the reaction to stop, the runaway reaction. The quickest way to achieve this and still maintain hydrogen pressure in order to minimize coke formation is to remove the feed from the unit, okay? And to cool the catalyst with the recycled gas. So you will remove the hydrocarbon, the feed from the unit. However, of course, you will have very well explained in the operating manual and procedures. However, if this temperature rise cannot be controlled, the unit should be rapidly depressurized to suppress the reaction and to minimize the danger of damage to the reactor and other equipment. If you can see that in the refineries and in the oil industry, there have been a lot of accidents related with the temperature runaway. Because, of course, if you reach the design temperature of the main equipment, you can have a failure of the equipment and a loss of containment of the equipment. You can have leaks and you can have fires related to this phenomenon. And of course, the very high temperature can also damage the catalyst. Okay, so it is important to follow always the operational procedure and to know the causes of these temperatures runaway in these kind of reactions that we have seen mainly in the hydrotreating and that we will see today or also in the online session today. That is the hydrotreating of the VGO, the vacuum gas oil. So this is was the idea to give you like the a little bit of background of this temperature runaway because you will see a lot when you will study from the operating manual and from the operating procedures. So that is the main concepts of the temperature runaway. Also, it is important to avoid this very high temperature during the startup and that we will see here, that we saw here, is to have a proper also here by overheating during the startup, a proper catalyst loading. Okay, you have had to have very careful to when your catalyst load to avoid any overheating in some places of the reactor. So this is a safety moment that we wanted to share with you. If you have questions about this temperature runaway, this is just a brief introduction to this phenomenon.
Guys, do you have any questions? شباب أحد عنده سؤال عن مفهوم التمبريتشر رانوي؟ هاي راح يعني تواجهكم خلال قراءتكم للأوبريتنج مانيوالز أو يعني بالبروسيس مال اليونتس يعني. No questions.
Okay.
No questions. Yeah.
So today we will start with this module that is the vacuum gas oil processing. We will see now what is the vacuum gas oil, but this module we will have 3 parts. This today we'll have the vacuum gas oil, this vacuum gas oil, you will see like VGO. Okay, so vacuum gas oil hydrotreating unit. Then next week we have the FCC and then the polynaphtha unit in next sessions. But today we will see the VGO hydrotreating unit. What we will see today, as usual, we will see where do we have the unit in the Carvala refinery scheme, the purpose of the unit, the main incoming and outgoing streams, the feedstock characteristics, the product, the schematic flow diagram, the chemical reactions, the catalyst, the process variables, and the reactor operating conditions. Okay. As you will see in this hydrotreating, we will have very similar reactions that we have seen in the previous hydrotreating process. So where do we have this vacuum gas oil hydrotreating? This is here. This is unit here, okay? Remember that the refinery, the first unit is the crude distillation unit, and the bottom of the crude distillation unit we will process in the vacuum distillation unit. And one of the main products of the vacuum distillation unit is the vacuum gas oil. Okay, this vacuum gas oil goes to this vacuum gas oil hydrotreating section. Okay, here you will see the capacity that is 36,000 barrels per stream day. Remember, all the units in this diagram, they are barrels per stream day. And this unit is an EOP technology unit, okay? So this is where is located the VGO hydrotreating unit in the Carvala refinery. Now we will see why do we need this hydrotreating. You can imagine the purpose of the unit because it is very similar to the other hydrotreating unit that we have seen, okay? So the idea, the purpose, let me go back again. You see here that we have the vacuum hydrotreating unit, and then we will have a fluid catalytic cracking unit to produce gasoline, okay? So as you can see, this model here of vacuum gas oil unit, the main purpose is to recover products and to transform some of this stream and produce gasoline. That is one of the main products of the refinery. So the major target of the vacuum gas oil hydrotreating unit and fluid catalytic cracking is to maximize the production of gasoline and to comply with the requirement of the 10 ppm weight of sulfur in the gasoline pool. Okay, this is a very specific restriction in gasoline, not to have more than 10 ppm of sulfur. In order to achieve this target, the VGO HDT unit has been designed to produce the feedstock to the FCC unit with less than 150 ppm weight to ensure the production of the gasoline from the FCC with less than 10 ppm weight of sulfur, okay? So with this quantity of sulfur at the outlet of the unit that we will see today, we have this quantity of sulfur in the gasoline that we will produce in the FCC unit that we will see in the next week. So the VGO hydrotreating unit is designed primarily to remove sulfur and nitrogen. But you know that if we have hydrogen and also the appropriate catalyst, we can also have the saturation of olefins and aromatic compounds. That will reduce this specification, that is the currents of carbon, and removing other contaminants such as oxygenate and organometallic compounds, as for the other hydrotreating unit that we have seen. So what is this specification here, this contrast on carbon? It is a laboratory test used to provide an indication of the coke forming tendency of an oil, okay? So if you saturate olefins and aromatic, you have less probability to have the formation of coke, okay? So this is the main purpose of this unit, okay? It is mainly to reduce the sulfur to this quantity, to 150. With this quantity, you will assure that the gasoline that you will produce in the FCC in the following unit, it will contain less than 10 ppm. So it can go to the gasoline pool without any problem. Okay, we will also remove nitrogen and we will saturate olefin and aromatics, and of course we will remove another contaminants. Okay, so this is the main purpose of the unit. We will see now more characteristic of the unit. But if you have some question about the purpose, because this is quite important, this slide.
let's check. شباب أحد عنده سؤال؟ هذه السلايد كلش مهمة لأنه توضح بالضبط شنو المطلوب من وحدة الفي جي او هيدروتريتر، شنو الغرض منها يعني. فاللي عنده استفسار أو سؤال خليه يرفع ايده أو يدز سؤال بالشات. Okay, we've got one questions. One question. أستاذ سجاد تفضل.
العفو استاذ احمد، بس تقدر توضح الرقمين مال 150 بي بي ام وال 10 بي بي ام، هذا الود سلفر
تمام. احنا ايش قلنا كمبدا اساسي انه الوحده شو تريد تسوي؟ تقلل السلفر الموجود بالفيديو. انت مو تجيب الفيديو من الفيديو، فهذا سلفر عالي. فانت الفيديو الغرض منه تريد توديه لوحده الاف سي سي. وحده الاف سي سي ما تتقبل السلفر عالي. لا تفهم قصدي؟ فايش قد الحد اللي تقبله الاف سي سي هو 150 بي بي ام. فالهدف من الفيديو تنزل السلفر مال الفيديو جاي من الفيديو الى 150 بي بي ام. هذا الهدف، واحده من الاهداف الرئيسيه لوحده الفيديو هيدروتريتر. ليش؟ لانه انت بالنتيجه بعدين شو تريد؟ الاف سي سي راح تعطيك غازولين. الغازولين حتى انت توصل، عندنا احنا غازولين بول نسميه. الغازولين اللي هو البنزين احنا نسميه بالعراق، يجيك من وحدات مختلفه مثل ما قلنا بالازمره، ويجيك من السي سي ار، صح لو لا؟ ويجيك من الاف سي سي. فالتارجت مالتك، الهدف الرئيسي كميه السلفر بالغازولين هي 10 بي بي ام. فانت هذا الهدف الاخير اللي تريد تحققه مال الغازولين بول. بس فيما يتعلق بالفيديو هيدروتريتر، انت 150 بي بي ام تحقق لك انخفاض بكميه السلفر، تنزل لحد 150 بي بي ام. واضح؟
عاشيرك استاذ احمد، عاشيرك التوضيح.
اوكي. Any more questions شباب؟ Okay, don't see more questions. I think we can move on here. Thanks.
Okay. So the feedstock, remember that we said that is coming from the vacuum distillation unit. Remember, this is the vacuum distillation tower, and this is our VGO product, okay? And we have these characteristics of this VGO for the two cases, for the two crudes. Case 1 was RAB and case 2 misreef. This is the TVP code range. We have this specific gravity. We have 2.5% of sulfur in this stream for case 1 and 4.3% of sulfur. So it is quite an important quantity of sulfur. We have also nitrogen, 850 ppm, and we have here 1000 ppm. We have aromatics in the feed, about 30% for case 1 and about 52.5% for case 2. We have also some metals that we have to decrease the quantity. And we have this a number that I explained before, the tendency of carbon formation, coke formation, that is this con-carbon weight percent, okay? So we can see here that we have, for case 2, well, 4.3% of sulfur in this stream, okay, that we will treat in this unit. So it is an important number that we have to reduce to 150 ppm. Okay, so this is the feedstock. Remember, that come from the vacuum distillation unit. This is the VGO, the vacuum gas oil. Okay, if we see, this is of course, you can find all this data in the process design basis for this unit. For the vacuum gas oil hydrotreating, you have all the data of the feedstock and the product specification. So what we will get, it is this, okay? We will get the vacuum gas oil that will go to the FCC unit. So this is our product. We will see here the sulfur content, that is 150 ppm. Remember that to convert from weight percent to ppm, you multiply 1, 2, 3, 4. So 100 ppm of sulfur. You can see here also a reduction of nitrogen. So we will have 12 ppm. We will have also lower content of this nickel and vanadium. That is very important because these are contaminants for the FCC catalyst. And we have also reduced this con-carbon weight percent, the tendency of coke formation, because we have saturated aromatics and olefins in the unit. Maybe we have not seen before this UPK. That is another way to characterize a fraction or a crude. We have here the explanation of the meaning of this UOPK, that it gives an indication of the saturation and cyclization. This value is a calculated value. So a high value indicates a more paraffinic saturated change hydrocarbon, while a lower value of 11.2 occurs for a more aromatic unsaturated cyclic stock. So when you have higher UP paraffinic feeds, will crack easier in the following unit, okay, in the FCC. And we have a higher conversion at the reactor temperature. And this is more or less how you will calculate this value here, okay? It is with the mean average boiling point of the fraction divided by the specific gravity. So we can see here that we will have mainly a saturated, paraffinic, more paraffinic than unsaturated. No, so it is good for the next unit, that is the FCC unit, because you will have a better product from the cracking of this unit. So how this was improved, because we have saturated some of the unsaturated components in the feed due to the hydrogen reactions that we will see later. But this is the main specifications of the product that we have from this unit. So if you focus on the sulfur, you see that we had at the feed we have 2.5%, here 4.3, and then we will have 150 ppm. Okay. So if you have some questions about the feedstock and the product or to the unit.
Yeah, just شباب بس عندكم استفسار؟ يعني شفت الفرق بين السلايد نمبر 10 و 11 differences between the feed and the product in terms of sulfur and the CCR, the Conradson carbon residue percentage إضافة إلى ال specific gravity وبقية المواصفات. أستاذ كرار، تفضل أستاذ كرار.
السلام عليكم أستاذ.
السلام ورحمة الله.
أستاذ بلد أحمد، ممكن توضح أن اليو أو بي كي؟
اليو بي كي هو بس انديكيشن انه مو اكو مثل الاي بي اي. الاي بي اي تقيس لك الدنسيتي
نعم.
بيست على سبيسيفيك جرافيتي، نفس المبدا. بس اليو او بي طبعا هي يو او بي هاي يعني من شركه اسمها يو او بي، بس عندهم هاي الطريقه يحددون بها يبين انه يعني كثافه المنتج مالتك كمقياس للمنتج للبرودكت مالتك، فيسموه يو او بي كي اللي هو شنو هو الترو بويلينج بوينت، ايش قد نقطه غليان هذا المنتج
نعم.
اس 1/3 على سبيسيفيك جرافيتي على الدنسيتي مالته. يعني هو ربط بين البويلينج بوينت والسبيسيفيك جرافيتي، طلع القيمه هاي تعتبر يسموها يو او بي كي، يعني انديكيشن للدنسيتي مالتك.
اسمح لي ابو يوسف.
نعم تفضل استاذ.
تسمح لي استاذ احمد.
تفضل استاذ عودة.
استاذ العفو، هذا فد انديكيتر لمكونات الفيد مالتك. اذا زاد ازيد من القيمه 11.2 يعني الفيد مالتك غني بالبارافينات.
نعم.
يعني راح يصير سهل لك الفيد اللي راح تعطيه الاف سي سي انه تحوله الى غازوني. واضحه؟ اذا اقل من هذا الرقم 11.2 دلاله على انت عندك ايش عندك اروماتيك. ماشي؟
هو استاذ يعني
اقرا
شوف اذا تريد يعني
اقرا التعريف وتحت تعرف
اكو هذا اللي بلوك ماكو اللي موجود المربع اقراه.
نعم.
استاذ كرار اقراها هاي، بس يعني شنو بوقت هسه من تخلص المحاضره عندك اقراها وشوف التعريفات وشنو معانيها يا حتى تكون عندك الصوره واضحه يعني.
بالضبط. احنا شو نسوي مثلا بالنفثه كنا ناخذ شيء اسمه البول، العفو البونه، يعني بارافين اولوفين نفثين اروماتيك. ماشي؟ بالمحاضرات السابقه ايش قد شنو اللي هو على
اوكي صور ديسكونكت.
العفو استاذ، السلام عليكم.
السلام، هلا استاذ امجد تفضل.
استاذ بس يعني في فاكتور خاص باليو بي لو مقياس عالمي هو هذا؟
لا هي اضافه يعني
هذا لا باليو او بي فقط.
اوكي شكرا جزيلا.
بهاي الوحده للاف سي، يعني يو او بي كي لهاي الوحده. هذا الكي مثل الثابت مالتهم، يعني هو الجذر التكعيبي للبويلينج بوينت على السبيسيفيك جرافيتي مال الفيد.
اي بس هو لا، بس سؤاله كمفهوم هو مفهوم هم شائع، يعني انت ممكن
نعم.
اذا وحده اكسنز الفرنسيه هم موجوده هاي القيمه يعني.
بالضبط. هم اسمها يو بي كي.
اي يو بي يعني مو لانه هاي اللايسنسر يعني اقصد ماكو ربط بيناتهم. اليو بي ماشي يعني كمواصفه يعني موجوده نفس الفكره، هو انديكيشن يعني.
نعم.
يعني مو اختصار. نقدر نعتبره مقياس عالمي يعني مشون عليه.
هو مواصفه، هاي مواصفه عالميه.
مواصفه لنوعيه الفيد.
لا البرودكت، هذا البرودكت الطالع، شوف البرودكت سبيسيفيكيشن. نعم.
اوكي
شوف ابو يوسف اقرا التعريف.
برودكت لا بس تقرا الفوق بدنا نحكي احنا
هسه. The toluene fraction gives indication of its saturation and cyclization. This is value is calculated rather than the measured quantity. A high obic value 12 indicate شنو؟ A more paraffinic.
صحيح.
اوكي؟ يعني saturated chain. hydrocarbon. while lower more aromatic unsaturated stock.
صح صحيح.
اي بس انا اقصد higher UOB
القيمه على البرودكت
بارافينيك فيد
تيبل مالتك
crack either yield higher conversion a given reactor temperature. يعني للفيد مالتك شلون راح تتعامل وياه.
اي بس انا شنو قصدي؟
حتى تطلع البرودكت.
انت اي بالضبط، بس هاي المواصفه اللي قدامنا نشوفها هسه
نعم.
بالسلايد هي ما يتعلق بالبرودكت، يعني البرودكت مالتك هذا بالبصره مشرف بصره كل شخص 12.5.
نعم 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 نعم.
بالمشرف 12.04. فاذا انت ترجعها قبل التفاعل تختلف القيمه اكيد يعني.
نعم.
لانه انت حسنت هسه مواصفته، صح ولا لا؟
تمام.
تمام. شكرا جزيلا استاذ عادل.
حبيبي.
Okay. More questions? I don't see more questions. I think Pilar, sorry to keep the
No. I understand.
Yeah,
Well, but this is about this. You will also find this as a characterization factor. Some people call Watson factor, but of course we are talking here about UP units, so
but it's indicative.
But is the same? No?
Yeah,
That you
it's
can
indicative.
find with different names.
That's right. Yeah.
Okay.
No, thanks.
Okay, so if we see the main streams, we have the VGO from the vacuum distillation unit. They also mix with some VGO from the storage. We have high purity. In this case, we don't use the hydrogen from the catalytic reformer, but we use high purity hydrogen from another unit that is a pressure swing absorber. That is a very high purity hydrogen. And then we will have these products from the unit. The main, of course, that is the converted gas oil that we will send to the next unit, that is the fluid catalytic cracking. We'll send also some to the storage. We'll have diesel. We'll produce some diesel to fuel oil blending. We'll have some unstabilized naphtha that we will send to the naphtha hydrotreating unit. And we will have some sort of gas that we will send to treatment for the sulfur removal to be consumed as fuel gas. This high purity hydrogen here, we will here goes to some compression stages, and then some of this hydrogen will be sent to the polynaphtha unit. Okay, but these are more or less the inlets and outlets of the unit. So this is our main product, and we have some other products from this hydrotreating unit. So we will see here the schematic flow diagram. This is this schematic flow diagram is in the operating manual, so I put it here because maybe it is easier to follow the process here with this type of flow diagram. We will go step by step. So the feed, remember, from the vacuum distillation unit passes through the feed filter and then enters the feed source drum. Liquid feed is preheated separately with the reactor effluent exchanger before combining with the recycled gas. So you see here, this is the source drum. You see here also the names of the main equipment. This is the source drum. Then you go through with a pump and you preheat the feed to the reactor. Then the preheated feed is mixed with the preheated recycled gas. The combined feed stream enters the charge heater to reach the desired reactor inlet temperature. So here you will mix with this recycled gas, that is the hydrogen, and you will go to this charge heater to obtain the desired temperature for the reaction. The reactant, okay, enters the top of the reactor. In order to operate the catalyst bed in an optimized temperature range, cold quench derived from the recycled gas are injected between reactor beds. Okay, It is not clearly shown that we have three beds, but you can see here that we have here the quench, okay? That is the same recycle, but without this preheating of the recycle. So some of this recycle goes here and is injected in the reactor as quench. Remember the importance of this quench we saw in the safety moment. We have to avoid any temperature runaway in the reactor. The hot effluent from the effluent heat exchanger is collected in a hot separator here. Well, you have to follow this stream, goes here, then goes here, and then goes to the hot separator, okay? Here you see that we have two phases, okay? So let's see what happened with these two phases. The hot hydrocarbon liquid is sent to this vessel, that is the hot flash drum, and the hot hydrocarbon vapor is used to preheat the stripper feed, the reactor feed, and the recycled gas. And then it's partially condensed in the product condenser, okay? So it goes here. Water here is injected in order to prevent the deposition of salts that can corrode and foul the coolers, as we have seen in the other hydrotreating units of the refinery. So the cold effluent from the product condenser is collected here in the cold separator. Here you have three phases. You can see here one, another, and another one, okay? As always, this salt water we will send to this cold flash drum, and then we will send for treatment, okay, to remove the sulfur in this salt water outside of this unit, okay? It is in another unit in the refinery. Then the cool hydrocarbon liquid is mixed with the hot flash stream from the hot flash drum and sent to the cold flash drum here, okay? You see here that it is cooled and it is combined with this and enters here in this cold flash drum. So the cool hydrocarbon vapor, this is the recycled gas, is routed to the recycled gas scrubber for H2S removal. Okay, here you will have, of course, the hydrogen, okay, that comes from the reactor, but you will have mainly also another light component and H2S. In this case, you don't want to send back here H2S, so you have this scrubber here to remove the sulfur in this stream. In the cold flash drum, so three phases are separated: the sour water that we already talked, off gas, and liquid hydrocarbon that will go to the stripper. Okay, that we will see in the next slide. So this is the first section of the unit, that is the reactor section. You heat the feedstock to the appropriate temperature to reach the desired temperature of the reactor. Here you have the quench of the reactor, and here you have the recycle that also will go to the reactor, okay? Because it will mix it with the feed here, okay? Before this charge heater. And then the process continues to separate the lighter components and the heavier components. So We will now go to the stripper column. So we have the stripper column here. That is, of course, needed to remove the H2S and light component from the stripper bottom product in order to meet the specification in sulfur content. So here we have the stripping steam.
Sorry, Pilar. Let's if we've got a few questions on the reaction side rather than we just move to the fractionation.
Okay.
It's difficult
Sorry.
to combine together. Yeah. شباب أحد عنده أسئلة أو استفسار على الرياكشن سايد مال وحدة الفي جي او اللي هي يعني شرحتها هسه بيلار؟ أحد عنده سؤال أو استفسار؟ شنو اللي صار لحد هسه؟
استاذ احمد اذا شفت الشات اكو سؤال.
السؤال ما انا
ما افتهمت استاذ حيدر من هو؟
لا هو ست ابتسام اللي سأله.
اي بس سأل استاذ حيدر ياهو.
ما لا بس هو شنو يعني مفهوم الباي باس شنو يعني هو
اي بشكل بسيط كتابه بس خاف تقصدني انا ولا حيدر.
ما ادري خلينا نسالها ست ابتسام سمعينا بس اي دقيقه.
خل اكتب لها انا ذا هاي.
لا دقيقه مو احنا المشكله تعرف شنو استاذ عدي ونصيحه للاخوه الكتابه تسوي ديستراكشن يعني تاخذ كل شخص من المحاضره يروح للشات فقدر الامكان احنا نعطي فرصه انه تسالون مباشره يعني. اي سؤال حتى اذا ما له علاقه بالسلايد.
خل تسال ماكو مشكله.
تفضلي ست ابتسام شنو سؤالك بالضبط؟ اذا سمعيني. سويت لك انا ميوت فاذا عندك سؤال اي نعم تفضلي ست.
السلام عليكم.
السلام ورحمه الله عليه وسلم.
السلام.
استاذ مو حضرتك استاذ حيدر لو مصطفى؟
انا احمد اسمي.
احمد فرحان.
ماكو فرق وماكو
ان شاء الله كلكم واحد ان شاء الله. هو يعني حقيقه شويه عالق بذهني هالسؤال يعني فرد يعني شنو مفهوم الباي باس يعني بعيدا عن
اي ماكو الباي باس يعني انه انت مثلا فلو هسه خلينا نقول عندك معده مثلا مبادله حراريه هيت اكسشينجر عندك فالفيد اللي راح يدخل للمبادله الحراريه ممكن على المبادله الحراريه اكو باي باس يعني شنو هو اللاين الداخل للمبادله قبل ما يوصل للمبادله ينقسم قسمين قسم يروح للمبادله وقسم يعبر المبادله يعبرها شنو انه يعني انت كعندك خيار انه ممكن الفلو تدخليه على المبادله او ممكن ما تدخليه على المبادله مثلا اذا الجو مثلا بارد مثلا بالشتاء فما احتاج ابرد باستعمال المبادله فالفلو كله اسوي له باي باس وين يروح باي باس اللاين يعني هو مجرد فالف ولاين يعبر المبادله من غير دخول الفلو بالمبادله الحراريه واذا احتاج
يروح معده ثانيه يعني
اي كمعده ثانيه او حتى مثلا اكو كنترول كل الكنترول فالفات الموجوده المسيطرات عليها باي باس الباي باس مثلا صار خلل بالكنترول فالف حتى الوحده لا توقف او الفلو لا يوقف اسوي له باي باس يعني ما يمر على الكنترول فالف
ممر جانبي ابو ممر جانبي
نعم واضح
ممر جانبي
يتنصب على اي معده مو الا الهيت اكسشينجر
معده كنترول فالف لاين يعني اي شيء يعني
ممر جانبي اتجاوز الخط الاصلي اتجاوز
تمام
باي باس باي يعني فرعي باس يعني مسافه
وضحت الصوره مشكورين تسلمون.
اوكي اني مور كويستشنز شباب على الرياكشن سايد مال البلوك دايجرام او البي اف دي. تفضل استاذ امير. يس يو كان اسك دايركت نو بروبلم.
السلام عليكم استاذ احمد.
السلام ورحمه الله عليه وسلم.
بالنسبه للهوت سيبريتر والهوت فلاش درام
كولد والهوت
الهوت سيبريتر والهوت فلاش درام اي اثنيناتهم يطلع هذا توب يعني برودكت هذا البرودكت غاز لو ليكويد لو شنو
Pilar, the question is from the hot separator. Is the outlet is it liquid phase or gas phase or two phase?
We have here two phases. We separated the vapor phase.
Vapor, yeah. So
It goes here and it cooled here, and the liquid goes to the hot flash drum.
Okay.
Okay, so why we send for hot separator top product, we send it to cold separator. This heat exchanger.
We send it here, we cool it, and we send it to the cold separator.
We send it, yeah. And another one, the hot flash drum, we send the top product to cold flash drum.
Yes.
I just want to know what's the difference between each of them.
Well, here you will.
Why we send for cold separator each, yani together? Why we separate them?
Yeah, you mean why not the same drum? You mean, yeah?
Yeah.
Okay, Pilar. So the question is, yeah. So you've got where you indicate now why this goes to the cold separator, and the other one it goes to the cold flash drum, not on the same drum. So that's the question. Why it's not the same drum?
Here in the first separation, you will recover most of the hydrogen that you will send it back to the reactor. Okay. You have here the first separation that will be the lighter components, okay, that you will recycle back to the component, to the reactor as a quench, and also to join the feed here. And then the other ones will have here, and then you will have here more methane, etanes that will go to the off gas that will be treated for fuel gas.
Yeah. So yeah, you are right. So basically, Ustad Amir, the difference is the cold separator objective is to recover the hydrogen, and then you recycle gas. Okay. So that's just hydrogen. It's nothing to do with the off gas. The second one is you've got off gas. The off gas is something that is has got like
more heavy, so we can use it for off gas.
Not hydrogen. So this one, the focus is to recover the hydrogen.
Yes.
Okay. Thank you. Thank you, Bilal.
Welcome. So you can see here that we got this liquid and this liquid that will go to the next column that we will see, okay?
Okay, Pilar, you can proceed.
Okay, so we will go to this stripper column we will remove H2S and lighter compounds, of course. So we will use stripping steam here. And we will have this top and this bottom product, okay? So the stripper overhead vapor is partial condensed in the stripper overhead and stripper trip condenser. So you have here an air cooler and a cooling water heat exchanger. And then you have here, of course, your reflux drum. Oh, they call it the stripper receiver. Okay, this is the stripper receiver. So the condensed hydrocarbon that is here is returned to the stripper as reflux, and part is sent as for the naphtha hydrotreating unit. Okay. Here you will recover some of gas also that we will be treated and used as a fuel gas. As always in this type of separator, you have this wood for the water to be separated and will be sent to another unit to be treated. Yes, and this all when you see here the off gas in all these units, we will see later in another online session that is a unit dedicated to treat this off gas to remove the sulfur content before being used as fuel gas in the refinery. Okay. So the stripper bottom, this liquid, it is hot and is sent to the product fractionator. Here we have a stripping steam also in this fractionated. And here you will like also to separate some lighter components and to give your product that we will here get our product. Okay, so the vapors leaving the product fractionator are condensed and collected in the product fractionator receiver. Okay, part of the condensed a hydrocarbon is returned as a reflux. The remainder is also the naphtha product that we will use to the naphtha hydrotreating unit. The water phase is separated in the product fractionator receiver and can be used also as part of the reaction wash water or sent to the sour water recovery. That remember that before we sent some water addition, so some of the water can be used to this purpose. We have here a side cut that is this diesel stripper. So it is the diesel that we saw that we will get from the unit. And this bottom is our product, our main product, that is the hydrotreated gas oil that we will send to the FCC unit, or of course to the FCC feed tanks. Okay. So this is the main purpose of the fractionation section, as always, to remove the lighter compounds that we still have in these two streams. Remember that we have two streams coming to this column. So the idea is to remove H2S and lighter compounds. We use stripping steam in both of the units. So we have water, of course, that we have to remove in these drums. And then we have here a side cut that we use as diesel. We also have like a diesel stripper that we had as we had in the crude distillation unit. Also is to get the adequate flash point of the product. And we have here our product that we can send it to the storage tank, of course, or directly to the FCC unit. Okay, but this is our product that we get with the specific sulfur content that we saw in the product specification, that we will have here maximum 150 ppm of sulfur. We have here 12 ppm of nitrogen. We have also decreased metal content. We have saturated some of the aromatic and the olefin content, and we will see now the reactions that take place in the reactors that for this product to be as we need for the following unit, that is the FCC, the fluid catalytic cracking unit. So this is more or less the scheme, very similar to other schemes of the fractionation section. The idea is to remove lighter components from our final product. So if you have some questions here.
اوكي شباب، احد عنده سؤال او استفسار على موضوع الفراكشنيشن، شنو اللي صار بيها؟ I don't see any questions so far.
Okay,
so I think
perfect.
it's clear, yeah. So we can proceed. Yeah, thanks.
I would like to talk because we have seen the reactor. Of course, that is a quite important piece of the treatment. And to explain why do we have separate beds in the reactor. We will have 3 beds in the reactor. We will have 2 reactors in this VGO hydrotreating. So You will see here a schematic of the reactor. We have the feed and the hydrogen, and going first to one catalytic bed, to another catalytic bed, and to the final catalytic bed. So you know that here we have liquid and gas, okay? If the gas and liquid flow become poorly distributed part way through the reactor, the catalyst will not be effectively used. So the idea here, if you have very good distributors of the liquid and the gas that fits the reactor, and here between each bed you will have the quench, but you have also the distributors, okay, that will ensure an adequate flow to the catalyst. So by separating a reactor into multiple beds with redistribution trays in between, the reactants exiting one bed are redistributed evenly across the cross-sectional area of the next catalyst bed. Very complicated, but it's the way that it will again redistribute, and in this way, should there be a problem with the distributor in a bed, the catalyst in the lower beds will be effectively used. If for any chance you have here a bad distribution, here you will solve the problem because we have a redistribution trace that will make the flow goes.
Sorry, Pilar, the voice is not clear. You know, it's difficult to figure out what the wording. I think the speaker again, I think.
Let me try again to put it now.
No, try to talk and see.
And now can you listen?
Yeah, but there is like kind of echo in the voice. So when you explain the paragraph, it becomes not clear, you know.
And now, if I put here the microphone?
Yeah, now is a bit low, but it's clear. Yeah.
Okay. So let me. I was telling that the reasons for separating a reactor into separate beds are the following. If the gas and liquid flow become poorly distributed partway through the reactor, the catalyst will not be effectively utilized. Remember that we have here mixed phase reactions, we have liquid and gas. So if we have poor distribution across the catalyst, you will not be using the catalyst effectively. So by separating a reactor into multiple beds with redistribution trays in between, the reactants exiting one bed are redistributed evenly across the cross-sectional area of the next catalyst bed. In this way, should there be, if you have a problem with the distribution in one bed, the catalyst in the lower bed will be effectively used. So this redistribution tray, there are special equipment pieces that will ensure that you will have an evenly distributed flow to the follow bed, okay? So here also we have these quenches. So in certain situations, the heat of reactions, as we saw in the safety moment, will be large enough that their temperature increase across a reactor will be greater than the design. If this were allowed to happen, a reaction could become unstable and result in the temperature runaway. Therefore, cold recycled gas is brought into the reactor at the interbed quench point in order to cool the reactant and control the reaction rate. So if you have here in this drawing, you have the feed, you go here through the catalyst, and you have the quench. If you have here, you see here this diagram of the temperature versus the reactor, you see here that the temperature increases because you have the exothermic reaction, but then the flow will be mixed with this quench, so you will decrease the temperature. Again, in the second bed, you will increase the temperature and cool, and you go like this, okay? So these quenches will allow you to have a better control of the temperature inside the reactor, okay? And of course, you will have also these redistribution trays that will, of course, you will first mix the quench with the outlet of this bed, and then you will find a redistribution tray that will redistribute the feed in an uniform way to the catalyst, okay? So that's why in this kind of reactor you have multiple beds, okay?
Okay.
So that's was the intention to put this slide, not to because maybe we can see why don't we have one only bed in this reactor, but these are the main reasons why we have a reactor in separate beds. So I don't know, of course, here you don't have you don't see the details, the mechanical details of these trays and how the quench enters, but okay, you will see in other sessions when you study the operating manual and you can see the data sheet of this equipment, the special pieces of equipment that you have here to accomplish this the mixing of the quench with the outlet of the catalyst of this bed, and then the redistribution to have an equal flow to the following bed.
Okay. I think let's just ask questions. The problem, the voice wasn't that clear, so let's see if we give a chance to the trainees to see whether they picked up the whole, idea of the quench business. Yeah. شباب افتهمتوا الغرض من الباراجرافز الموجوده اللي هنا 3 باراجرافز عندنا بهاي السلايد، واضحه لو مو واضحه؟ المو واضحه يرفع ايده يعني يسال سؤال معين اذا عنده شيء مو واضح يعني.
استاذ عفوا بس توضيح للنقطه الثانيه.
second point redistribution. The second point is related to the first point. What happened in the first point? We are saying if the gas and liquid, الغاز شنو عندك اياه استاذ؟ الهيدروجين صح؟
الهيدروجين اكيد.
اي والسائل شنو عندك؟
الفيد هو الفي جي او.
فشنو الكلمه تقول بالاحمر هي كاتبتها poorly distributed. شنو poorly distributed؟
توزيع ضعيف
بالضبط. فهاي شلون انت تحل هذا الاشكال؟ ده تقول لك شو يسوي؟ اكو quenching by separating a reactor. مو هسه احنا الرياكتر اذا تشوف الرسم مقسم الى 3 بد صح لو لا؟
صحيح.
فالغرض واحده من اسباب انه مقسم ليش حتى الرياكتر into multiple beds with redistribution trays، فيسوي redistribution. الريديستريبيوشن حتى يخلص من موضوع عمليه يعني مجانسه السائل مع الغاز، حتى انت بالنتيجه تحقق التفاعل. فانت لو تقراها الفقره الثانيه by separating a reactor into multiple beds with redistribution trays in between the reactants existing one bed are redistributed evenly across the cross-sectional area of the next catalyst bed. In this way, should there be a problem with distribution in bed, the catalyst in the lower beds will still be effectively utilized. فأنت يعني إذا أنت عندك التوزيع اللي بين السائل والغاز حتى أنت يصير التفاعل الافشنسي مالته عالية، فالبد الثانية إذا صار بالأولى عندك إشكال فما صار توزيع، فش تسوي؟ انت تقدر تعوض هذا الخلل بالديستريبيوشن بين الكاتاليست والمواد المتفاعله. انت عندك البد الثانيه راح تحسن لك الافشنسي مال التفاعل.
بها ابو يوسف صينيه توزيع، صينيه دكتور مالت صينيه توزع التغذيه على الكتل بالبيد الاول والثاني والثالث، الدخول عن طريق صينيه التوزيع.
نعم.
صينيه قبق فوق الكتلز، قبق.
نعم.
قبق صينيه توزع مثقبه، توزع التغذيه بالتجانس.
بالضبط، هو السبب انه لذلك عندك 3 بيدز،
3 بيدات بالضبط. هم عالجنا سالفه الافراط بالحراره لان تفاعل اكسوثيرمي.
يعرفها
عن طريق الكوينشنج والتوزيع، هذين الثلاثه. عالجنا سالفه التوزيع، يعني ماده تدري غاز ماده ثقيله، مو سهله التبخر والتوزيع، فعالجناه التوزيع بيش بصينيه التوزيع.
نعم صحيح.
فكل الامور عالجناها بهاي التصميم يعني الداخلي الميكانيكي للمفاعل، 3 بيدات ويا الكوينش ويا صينيه التوزيع، عالجنا كل المشاكل حتى يصير تفاعل كفو.
تمام. استاذ مصطفى تفضل. اذا تسمعني تفضل استاذ.
السلام عليكم استاذ.
السلام ورحمه الله.
استاذ بس ما خصك، بالنسبه للكوينش غاز احنا نضخه اثناء العمليه حتى لا نصل للتمبرتشر ران اواي، لو فقط من يصير عندنا تمبرتشر ران اواي نضخه حتى يبرد.
خلي اعطي السؤال البيلار. the question from Mr. Mustafa is about the purpose of the quench. Is it continuous or it's only needed when we reach the runaway temperature?
No, it is continuous.
Okay.
We will have, when we will see the PFD, that is a temperature control in the reactor that will open the quench more or less, but it is a continuous.
Okay. Thanks. So مصطفى واضح الجواب لو اشرح اللي قاله؟
واضح. العمليه مستمره للضغط.
بالضبط مستمره، وبدليل انت شوف الجراف اللي هي حطتها النكست للرياكتر. الجراف شو يسوي؟ انت الجراف تصعد الحراره يزيد الحقن مال الكونش، يرجعه يبرده، ترجع الحراره تصعد وهكذا، فهاي مستمره العمليه.
زين اذا صعد وضخينا كوينش غاز وظلت يعني درجات الحراره مرتفعه، اكو عمليه نقدر نضيفها اضافيه؟
بالضبط. اذا انت وصلت الرنوي وصارت يعني بديت
هذا افراط شت داون، لازم يقطع الفيد.
لا مو العفو استاذ عدي، مو شت داون. تسوي قبل الشت داون عندك لاير اوف بروتكشن، تسوي دي بريشرايزيشن.
هو يقطع الفيد وبعدين دي بريشرايز ويبرد
بريشرايز. اي بس مو مو مرات اذا انت دي بريشرايز عندك تقريبا 15 minutes to دي بريشرايز، فاذا يعني صارت اندر كنترول ترجع طبيعي، بس مو
ترجع تدخل الفيد. هو اول شيء يقطع الفيد.
اي بس
يقطع الهيدروكربون. يعني قصدي هو مو شت داون،
ما اقدر اطبق
يعني نقطع الفيد.
اي بالضبط. بس
هو
انت ما تسوي، يعني اقصد شنو، انت عندك انت صار رنوي وعندك شت داون، بس اكو بتوين الشت داون والرنوي سوي ديبريشرايزيشن. الديبريشرايزيشن حتى تخلص من الفلو الموجود عندك الانفنتوري بالرياكتر تقلله. عاده احنا من نصمم الديبريشرايزيشن تنزله خلال فتره 15 دقيقه، فتصاميمنا للديبريشرايزيشن سيستم بيست على 15 minutes. حلو. قبل ما توصل يعني اذا طبعا اخر شيء اذا هو يصير شت داون.
هو هذا هسه افتراض من الاستاذ، يعني هو الافراط بالحراره، بس يعني اكو هيك شيء.
لا بس السيستم مصمم، يعني
مصمم لهيك التعامل ويا هذا الموضوع.
بالضبط. وعندك كوانشنج، هو انت يصير كوانشنج يستمر، يفتح بعد هيدروجين اكثر
طبعا. هو ما دام تفاعل اكسوثيرميك يعني واضح لازم يصعد حراره.
واضح استاذ مصطفى؟
واضح استاذ، مشكورين.
Any more questions? معك اسئله؟
بني استاذ.
تفضلي ست ملاك.
بيس ابونيوس مستر احمد عن سيد أداي. استاذ I'm sorry, I don't understand what means quench.
Pilar, if you answer the question.
The quench?
Vale.
Yes.
What does it mean? Yeah, so if you...
The quench is a sudden cool, or so when you cool down something quickly. Okay, so this is the idea of this quench, is to cool this outlet of this bed, to cool it with this hydrogen, with this same hydrogen, but remember that we preheated this hydrogen before mixing with the feed. So this quench will be the same hydrogen, but without preheating, okay? So from the compressor, directly from the recycle compressor. So this quench, it is a cold quench, 70, 90 degrees. We can see later also in the PFD. So it is to cool this stream And this is the meaning of quench. When you cool down something quickly, there is a quench. Okay.
اوكي كل يعني
هو
واضح
يعني تبريد مفاجئ، تبريد مفاجئ سريع.
هو مثلا هسه لا سمح الله عندك مثلا صار حريق مثلا بالحديقه، نار شويه صارت، فش يجيب واحد يجيب مثلا سطله مال مي ويذب المي راسا على الحريق، فش هذا الكونشنج يعني. بس مفاهيم متعدده يعني. هذا هنا انا شويه تكنولوجيا اكو معقده، بها هيدروجين وبها رياكشن يعني، بس هي عمليه انت اطفاء الشيء يعني.
Yes, I know. Two question paragraph between reactor length and temperature. Explain.
Here.
Yes.
So if we start here, then we will start to increase the temperature. Remember, because you can have an exothermic reaction. So if we see here, you have temperature here, so you will start to increase the temperature. Okay, and
decrease?
Then increase the temperature because you have an exothermic reaction. Then you will find the quench. Remember that the idea is to cool down, so you will decrease the temperature. Okay.
Yes, I know. Thank you.
Okay.
Yes, I know.
Thanks, Mrs.
Thank you.
Thank you.
I think it's time to take a break. I think let's take 20 minutes break.
Okay.
Yeah.
Okay.
And then we come back because we are halfway through the presentation.
Okay. Okay. Perfect.
بس استراحة في 20 دقيقة. Okay. Hi, Pilar. Sorry, you can proceed now with the next slide. Thanks.
Okay. Perfect. So we will see now the reactions. Let's see some facts about the reactions. The hydrotreating reactions are catalyzed by the metal sites on the catalyst. The primary hydrotreating reactions are sulfur and nitrogen removal, as well as olefin saturation. The product of these reactions are the corresponding contaminant-free hydrocarbon. So you will eliminate the contaminant along with H2S and ammonia. So you will have the free hydrocarbon and you will have H2S and ammonia formation. Other treating reactions include oxygen, metals, and halide removal and aromatic saturation. In each of these reactions, hydrogen is consumed and heat is liberated. As we have seen, these are exothermic reactions. So the reactions are the same that we have seen in the different hydrotreating of the units that we have seen, the naphtha, the kerosene, the diesel hydrotreating. So let's see them again. So for the sulfur compounds, what kind of sulfurs we can find? Mainly mercaptans, sulfides, and disulfides, but we can also have some cyclic sulfide and some thiophenes. So the reactions are the following. You will react the mercaptan. Remember that this is a mercaptan when you have an alkyl group and SH here. Anything here, here we have 6 carbon, but it can be 7, 8, what else? It will be a mercaptan because it has this SH. Will react with hydrogen, and you will have the corresponding hydrocarbon without sulfur plus H2S. If you have a sulfide, that is that you have carbons here, carbons and 1 sulfur in the middle, in between the carbon chains, and you react with hydrogen, you will have the hydrocarbon without the sulfur plus H2S. The same if you have disulfides, so instead of 1 sulfur, you have 2 sulfurs. You react with hydrogen, you will have this hydrocarbon plus H2S, and this is the same for the cyclic sulfide and for the thiophene. You have these compounds plus H2S. So the typical feedstock to the VGO hydrotreating unit will contain mercaptan, sulfides, and disulfides. These compounds are easily converted to H2S. The feedstock containing heteroatomic aromatic molecules are more difficult to process. And the hydrotreated VGO sulfur content should be, remember, 150 weight ppm maximum. That is, they're required to have an FCC gasoline with 10 ppm. Okay, so these are the sulfur reactions. Remember, in presence of hydrogen at temperature and pressure condition and the adequate catalyst, you will have these reactions. Okay. For the nitrogen compounds, remember that we have seen this type of compounds. The same, you will have the reactions with hydrogen, but instead of H2S, you will produce ammonia. Okay? And of course, the hydrocarbon without the nitrogen. The nitrogen removal is more difficult than the sulfur removal, and the hydrotreated nitrogen content should be maintained below the 12 ppm weight. Okay. The ammonia that is formed during these reactions, it is removed in the sour water that we have seen in the process description. We can have also some oxygen compounds, and they will react with hydrogen to the organically combined oxygen is removed by the hydrogenation of the carbon hydroxyl bond, forming water and the corresponding hydrocarbon. Okay. We have seen also that during the reactions we will have some olefin saturation. These are very rapid reactions and have a high heat of reaction. And we will have some aromatic saturation also. So these are the most difficult, and they are very exothermic. We have also this halide removal. For example, here we have the chloride and the carbons, and we will react with a hydrogen, and will produce the corresponding acid and the hydrocarbon without the chloride. So this is much more difficult than the other reactions, and the maximum removal is about 90%. And also you will have some metals removal. We have seen that we have in the feed nickel and vanadium. So metals are retained on the catalyst by a combination of adsorption and chemical reaction on the catalyst bed. And typical metals that you will find are nickel and vanadium. This is very important, this paragraph here, because the total metal retention of the catalyst system can be increased by using a GAR reactor or GAR bed of catalyst, specifically designed for demetallization. Some demetallization GAR bed of catalyst are specifically designed for these reactions, and of course it will not be as good for the sulfur and nitrogen removal. Like it say here, no? That you can retain the metals, but this catalyst will have a lower activity for the other reactions. We will see when we will see the reactors now, the catalyst that we will use in the reactor, that we will have in one bed different types of catalysts. So the licensor have designed the reactor with 3 beds, but with different catalysts in each bed. Okay, and one of the reasons is this: you have guard beds to remove metals, and of course you have also other guard beds to have a proper delta P in the reactor. Okay, here we see the catalyst that we use in this process is an aluminum base, as we have seen in the other hydrotreating catalyst, with compounds of cobalt or nickel and molybdenum. That is the metal side. Usually there are layers of graded bed material on the top of the catalyst bed, and this is used to protect the main catalyst bed from fouling and poisoning. Okay. According to the design basis of the unit, the catalyst will have an operating cycle length of 2 years. Okay. And this is the shape of catalyst, quadrilobe catalyst. So now we will see the catalyst in each reactor, the quantities that we have, the volumes. But you will see different catalysts, and it's due to this, okay? We will have different layers of catalyst in one bed to protect the catalyst, and some catalysts that are specialized used to remove metals in the feed. So if we see the catalyst that we have in the reactor 1, we have the bed number 1. As you can see, we have all these type of catalysts in one bed, okay? So these specific catalysts are to protect the main catalyst, and also they have another properties to remove metals and to have a better pressure drop and avoid fouling in the catalyst. So you can see that it's not that simple, because you have a lot of catalysts in one bed. In this first bed of the first reactor, you have this total volume, okay? But remember that we have 3 beds in each reactor. So in the second bed, you have 3 types of catalyst, and you will have this quantity of catalyst in the second bed. And in the third bed of reactor 1, you will have this quantity of catalyst. So in the first reactor, you have this quantity of catalyst. You can see that there is a huge quantity of catalyst. These reactors are quite big. I think there are like 26-meter height, this first reactor, so there is a very important piece of equipment in the refinery. So it is important to see, for example, that you have here the main catalyst, but you have other catalysts, as we say, to protect the catalyst and to avoid fouling. And maybe in this case, for example, this 55, maybe it is good for the metal removal in the feed, okay? But of course, we don't have a lot of information of this, because this is very related with the licensor. But the idea of to have these different kinds of catalyst in each bed is, as we said before. No? This is for reactor 1, but of course, remember that we have 2 reactors. So we have reactor 2, the same, we will have 3 beds. In the 4th bed, that is the first bed of this second reactor, we'll have this quantity of catalyst. In the second bed of this second reactor, that is in total, there is the bed number 5, if we consider the 3 beds that we have in reactor 1, we'll have this quantity. And in the last bed, we will have this quantity of catalyst. So the quantity that we have in the reactor 2, we have 400 cubic meters, more or less, of catalyst. And in total, in both reactors, we have 725 cubic meters. You see that this reactor has a little bit more catalyst than reactor 1, and also the height of the reactor is 32 meters compared to 26 from reactor 1. So these are what is related with the catalyst. Okay, we have seen the main reactions. We have seen the type of catalyst that we use for this VGO hydrotreating, and we have seen the quantities that we will use according to the design of the unit by the licensor, okay, by the EUP. So if you have some questions about catalyst, because now we will continue with process variables. So if you have some question regarding catalyst, please.
Let's check here. شباب أحد عنده استفسار أو سؤال على الكاتاليست؟ I don't see any questions. I think you can proceed here.
Okay. So we will see now the main process variables of this unit. Okay, this data comes from the process design basis, okay, of the unit. So the main process variables are temperature, space velocity, hydrogen partial pressure, recycled gas rate, and also the makeup hydrogen and recycled purity. So we will see first the process, the temperature. Okay, so the reactor inlet temperature is the process variable most easily and commonly controlled by the operator to adjust the amount of sulfur or nitrogen removed from the bed. The inlet temperature must be controlled at the minimum required to achieve the desired product properties. Temperature above this minimum will only lead to high rates of coke formation and reduced cycle length. We will use here also, as we have seen in the other units, the weighted average bed temperature. Okay? So the gradual loss in catalyst activity can be compensated by increasing the reactor temperature up to this limit. In general, above this level, cracking and coke formation become very rapid and little improvement in performance is obtained. As we have seen, remember that when you lose activity, that you activity in the catalyst, you can compensate by increasing temperature. That's why in some cases we have the start of run condition and the end of run conditions for the process variables. So in this case, how we will calculate this weight average bed temperature? Okay, if we have several beds, we have here 5, but we have 3, but it's the same concept, and you have the amount of catalyst that you have in each bed. Okay, you have 10% for this example in the catalyst in the bed A, 25 in bed B, 30% in bed C, 25 in bed D, and 10 in bed E to have the 100% catalyst weight. And you have this temperature, this average temperature in each bed. So you will multiply the weight and the temperature, okay? Weight times the temperature plus the bed B and the temperature average in this bed and so on. And then you will have here the weight average bed temperature, okay? So that is the appropriate way to have this weight average bed temperature. So this is what is concerned to temperature. Then we will have the space velocity, as we have seen. So the amount of catalyst loaded into the reactor is based on feedstock properties, operating conditions, and product quality required. The variable that is normally used to relate the amount of catalyst to the amount of feed is termed liquid hourly space velocity, okay? LHSV. This is the formula that we have seen, okay? This is the volume of the feed at standard conditions divided by the volume of the catalyst. An increase in the liquid hourly space velocity will require higher reactor temperature to achieve a constant level of desulfurization, as well as higher recycle rate to maintain a constant ratio of hydrogen to hydrocarbon. The increased reactor temperature, remember, will lead to more coke, okay? And a reduction in the liquid air hourly space velocity may lead to a bad flow distribution through the catalyst. So higher temperatures will be required to obtain good product quality. So more or less, it is if we increase or we reduce this liquid air hourly velocity different from the design value that we have to handle, we will have to manipulate other variables to get the same product quality, but we will have more coke formation. Okay, remember that in the operating manuals, also the licensor will give you the instructions about the desired liquid hourly velocity that you will have to maintain for the unit. And this is the formula how we calculate this liquid hourly space velocity. This is divided, in this case, will be divided by the total volume of catalyst.
Sorry, Pilar, just let's give them time to ask questions.
Yes, please.
Too much to remember. شباب أحد عنده أسئلة so far على البروسيس فاريبلز؟ ترى هذه كلش مهمة الفاكتورز ذني، يعني ذني هن الأساسيات لتشغيل المفاعل. فأحد عنده سؤال أو استفسار عنها؟ مستر مصطفى تفضل.
السلام عليكم استاذ.
السلام ورحمة الله.
استاذ بس ملاحظتك استاذ، هسه هنا بالحالة الانكريز مال ال اتش اس في راح نزيد درجة الحرارة، ومن يكون نقصان عندنا بال اتش اس في هماتي راح نزيد درجة الحرارة.
شلون يعني؟ ما افتهم سؤالك والله.
يعني بالحالتين، يعني قيمة ال اتش اس في بالحالتين، بحالة التزايد او النقصان بالقيمة راح نزيد درجة الحرارة.
يعني هو انت الانكريز بالال اتش اس في والريكواير هاير رياكتور تمبرتشر، يعني اذا زاد مثلا شنو اللي زودته؟ زودت الفيد الداخل للوحده مثلا بير اور، يعني الفلو مالتك اذا زاد شنو يتطلب منك تسوي؟ زيد درجه حراره المفاعل to achieve constant level of desulfurization. ليش؟ otherwise راح يصير اضطراب عندك بالديسلفرايزيشن، فالسلفر اللي يطلق بالبرودكت يصير اعلى. تفهم قصدي؟
نعم.
واضح قصد الفكره اللي احكيها؟
واضح استاذ.
ليش؟ لانه انت شوف المعادله شو تقول؟ الفوليوم اوف فيد على الفوليوم اوف كاتاليست. فمثلا زاد عندك الفيد، شنو يتطلب منك حتى انت تبقي نفس الدرجه مال الديسلفرايزيشن، ازاله السلفر بالمفاعل؟ شو تسوي؟ تزيد الحراره.
بينما اذا نقص عندي، اذا نقص الفيد، قل الفيد.
اي، فشنو اللي يصير؟ اذا قل الفيد عندك راح معناها ريدكشن بالال اتش اس في، ما يليد تو باد فلو ديستريبيوشن.
هماتي راح نزيد الحراره.
لا بس اسمح لي هسه انت تقراها through the يعني وش راح يصير يصير اوقف خلي بيلار sorry the question is about the increase is clear the reduction in the LHSV which gonna lead to bad flow distribution through the catalyst, right?
Because
so what you need to compensate that again you have to increase the temperature.
Yes, it's the same. You have in both to increase the temperature, even if you increase it or you decrease it. So that's why important to keep the design liquid hourly space velocity that is recommended for the unit. Because in this, if you increase the LHSP, you will have lower residence time, so you will have poor lower reactions in the, so you will have to increase the temperature again, and here you will have a bad flow distribution, so you will have to increase the temperature also to compensate for this bad flow distribution through the catalyst.
استاذ مصطفى السبب الثاني انت يعني هي مو واحده عكس الثانيه، يعني شنو القصد؟ مو موضوع انت شو يصير اذا الفلو قل عندك، المشكله راح تتولد نتيجه انخفاض الفلو عندك مثلا، شنو راح يصير عندك؟ بالاحمر مكتوبه باد فلو ديستريبيوشن، بسبب الديستريبيوشن قل عندك، فايش راح يصير؟ كفاءه التفاعل راح تقل، فبالنتيجه واحده من المعالجات هاي المشكله انه انت شو تسوي؟ هم تزيد الحراره. تفهم قصدي؟
استاذ احمد عفوا على المداخله.
نعم.
هنا يمكن القصد انه اذا قل ال LHSV راح يصير باد فلو ديستريبيوشن، راح يقل عندي كفاءه التوزيع. بهالحاله ايش راح اسوي؟ راح ازيد ال LHSV، ازيد الفلو. من ازيد الفلو راح احتاج ازيد الحراره، يعني ترتبط بالنقطه اللي قبلها. مو يقول انكريز ال LHSV لازم انكريز تمبرتشر، يعني واحده مرتبطه باللخ. من تزيد الفلو لازم ازيد الحراره حتى احصل كواليتي جيد.
مو هيك التعبير انت عندك حالتين لل LHSV، واحده زائد وواحده اذا صار بها ريدكشن، واحده انكريز وواحده ريدكشن. المعالجات انت اذا هذا الحدث ظهر عندك شنو اللي تسويه كمشغل؟
ازود الفلو.
لا هسه مو انت قلل الفلو عندك، هسه عندك مشكله بالفلو قل عندك، فشنو اللي تسوي؟
مو هيك حصير عندي مشكله ثانيه بالديستريبيوشن بالتوزيع.
اي فشو تسوي حتى تحل هاي المشكله؟
يعني ازود الحراره.
بالضبط، يعني حتى اذا يعني اقصد هي شنو؟ الحدثين متناقضين بس الاكشن واحد. استاذ مصطفى واضح؟ استاذ مصطفى
يعني احنا بالحاله الاولى ما نقدر نقلل الفلو.
لا هسه انت بس اسمح لي، انت لن تشعب بالفرضيات الهوايه، هي يجوز اكو 10 اسباب لهذا الحدث، بس انت اذا زاد ال LHSV انت تزيد الحراره، اذا قل ال LHSV هم تزيد حراره.
تمام.
هسه شنو الاسباب اللي ادت الى هذا موضوع بحث ثاني
يعني ما نقدر نغير الفوليوم بدال الحراره.
تقدر كل شيء تسوي، بس القصد لو هذا الحدث صار عندك شنو هو واحده من الاكشنز تزيد الحراره حتى الديسلفرايزيشن ما يتاثر عندك.
واضح.
اوكي
واضح.
اوكي بلار ثانكس.
استاذ
سوري there is another question بلار just تفضل
استاذ. قلت اذا هاي نزود الفيد، حجم الفيد.
لا
زين استاذ احنا
عوف هاي المعلومه. عندك انت اشكاليه وين؟ انه ال LHSV زاد او ال LHSV قل. عندك اثنين سيناريوهات. هسه شنو السبب اللي ادى الى الزياده او النقصان موضوع ثاني، بس انت يعني طريقه عمل بالمفاعل حتى تحافظ على 150 PPM بالبرودكت مالتك تزيد الحراره. هسه شنو الاسباب موضوع ثاني هذا.
اوكي استاذ، بس السؤال انه الفيد اذا زيدته احنا ما عندنا تفاعل باعث للحراره.
نعم.
يعني هذا هم ياثر زياده الفيد على التفاعل لو لا، يعني الحراره هم تزيد او تقل؟
طبعا اذا زادت الفوليوم if the volume increase per hour this will lead to increase the LHSV and but when the flow increases it means desulfurization will be affected. يعني راح يصير تاثر بالشنو؟ بالديسلفرايزيشن اذا الفلو زاد عندك. فشلون تعالج هذا الموضوع حتى لا تخسر الكميه، يعني حتى لا تخسر كفاءه التفاعل وبالنتيجه كميه الكبريت الطالعه بالبرودكت راح تصير اعلى من المطلوب فتزيد الحراره. ها هي. اوكي استاذ أمجد؟ تفضل استاذ حسين.
السلام عليكم استاذ.
لا ورحمه الله وبركاته.
استاذ بس ملاحظه صغيره. زياده ال HSV يعني هو المعلومه كلها انه الفلو راح يزداد، من يزداد الفلو يعني الوقت المتبقي مع التفاعل، وقت التفاعل راح يقل باعتبار زايد الفلو تايم اقل.
نعم.
لهالسبب انا ازود حراره حتى ازود الاكتيفيشن.
زيد التفاعل زيد يعني
يعني ازود بالضبط ازود اكتيفيشن مع التفاعل حتى بهذا الوقت القليل اقدر احصل نسبه تفاعل نفس الوقت.
نعم. Okay. I don't see more questions, so I think we can proceed.
Okay.
Yeah, thanks.
Okay, so now we will see the hydrogen partial pressure. A reduction in operating pressure below its design will have a negative effect on the activity of the catalyst and will accelerate catalyst deactivation due to increased coke formation. The major control variable for hydrogen partial pressure is the recycled gas purity that should be monitored closely to assure it is always maintained above the minimum value. So here, well, but I put it that is stated in the operating manual, but it's like a remark that the reactor section operating pressure is controlled by the pressure that is maintained. Remember that we saw the cold separator in the process description. This pressure you multiply by the hydrogen purity and will determine the partial pressure of the hydrogen in the reactor. Okay, so that's why they explain where to control the pressure of the section that is in the cold separator, that you will have also and you will have the composition of the recycled gas, and you will multiply pressure by composition, and then you will get the hydrogen partial pressure. Okay. Another variable that is important is the recycled gas rate. So in addition to maintaining the partial pressure of the hydrogen, it is also important to maintain the physical contact of the hydrogen with the catalyst and hydrogen so that the hydrogen is available at the sites where the reaction is taking place. So you have to ensure to have a good recycle. So this is accomplished by circulating the recycled gas throughout the reactor circuit continuously with the recycled gas compressor that we have seen in the process description, and we will see it now if you want in the PFD. So you have to keep the partial pressure, but also you have to have a good recycle rate to maintain the appropriate content of the hydrogen with the catalyst and hydrocarbon. Okay. The standard measure of the amount of gas required is the ratio of the gas being recycled to the rate that fresh feed is being charged to the catalyst. Okay, so that's why they mention that how they calculate this recycled gas rate, the gas to oil ratio, that is the total circulating gas to the reactor divided by the feed to the reactor. Okay.
Sorry, Pilar, can you zoom in on the question because it's very...
Yes, because this is quite enormous. Okay. So this is also an important variable that they use to measure if you have an appropriate recirculation rate, that is the total circulating gas to reactor divided by the total fresh feed to the reactor. Remember that we have the circulation to the reactor that mixes with the feed previous to the heater. And we will have also the recycle that serves as quench to the reactor. So you will have to calculate this gas to oil ratio according to this equation. And this is the VGO to the reactor inlet in cubic meters per hour, okay? And they will give you an appropriate value to maintain for this gas to oil ratio. So as with hydrogen partial pressure, in any reduction of the gas to oil ratio below the design minimum will have adverse effects on the catalyst life. So these two are linked, and they are quite important, these three, okay? Because it talk about the recycle, the hydrogen in the recycle, and also the purity, okay? Remember that we saw the makeup hydrogen to this unit is from the PSA section. There is another unit in the refinery where you process some hydrogen and you get a very high purity hydrogen, okay? So the purity of the recycled gas, remember, that is part recycle and then you add some makeup. So it is determined by the following factor: the purity of the makeup, and of course the amount of light hydrocarbon and H2S that are allowed to accumulate in the recycled gas. Remember, we can see here the makeup hydrogen composition for this pressure swing absorber that is another unit in the refinery. Look at the quality of the hydrogen. It is 99.9% of hydrogen, okay? With less than 0.1% volume of methane. We don't have H2S, and we have less than 20 ppm of CO plus CO2. So it is a very high purity hydrogen used as makeup in the unit. The light hydrocarbons present in the recycled gas enter the system with the makeup gas in addition to those being formed in the reactor. Here we see that we have almost no light hydrocarbons. The H2S formed in the reactor can reach equilibrium values as high as 5% in the recycled gas, okay? Remember that in the reactions, the sulfurization reactions will produce H2S. So we can have, of course, H2S in the recycled gas. This concentration of H2S has a depressing effect on the activity of the catalyst, okay? Because if you recycle hydrogen with high concentration of H2S, will decrease the activity of the catalyst. That's why it is important the removal of this H2S, okay? We have seen in the process description that we have a scrubber for the recycled gas to remove the H2S, okay? Here we have the scrubber with this, and we use this diethanolamine solution to remove the H2S. So this is important that we have not seen in another hydrotreating unit, because here we have a lot of sulfur and we will have a lot of H2S formation, and that's why it is important. This very high purity of makeup hydrogen, and we also remove this H2S from the recycled gas. Okay, so this is related with the makeup hydrogen and recycled gas purity. I don't know if you have questions about these concepts before we go to the to see the PFD.
Let's check if we have questions. شباب أحد عنده سؤال أو استفسار على المفاهيم الأخيرة اللي حكيناها بالسلايدات الأخيرة؟
Maybe we can go a little bit to the because now knowing these concepts we can go to this. Okay, remember that when we saw the process description, this is the makeup gas that now we see that we use a high purity hydrogen, and you have here the recycled gas. Okay, that comes from here, come from this hot separator, and then goes to this vessel, to this screwer. Here in this screwer, we will eliminate the H2S in this recycled gas. Okay, and then we will go to the compressor, and we will join with the makeup gas and goes to the reactor as quench, or we will mix with the feed. So this is the screwer that we were talking about now, about that is important to have the appropriate purity in the recycled gas.
Yeah, that's good. Good that you explained it on the PFD.
Yes.
So let's see if there are some questions.
Yes, please.
شباب واضحة عندكم شنو السبب الموضوع اللي يتعلق بالبيوريتي مال الريسايكل غاز؟ أو عندكم أسئلة على هي المفاهيم الأخيرة الاثنين اللي بالبروسيس فاريبلز بالرياكتر؟ ماكو سؤال؟ Okay, so I will ask you a question. What happens if we don't have scrubber and we don't have amine? So what's going to happen? Why we need to inject amine, and even if we don't have scrubber, what's going to happen in the reaction and the impact on the reactor? Okay.
استاذ ما راح تتم.
لا بس دقيقة، بس العفو دقيقة، بس دقيقة، خلينا نشوف المجموعة اللي راح يرفعون ايديهم، بس دقيقة يعني. So we've got سعد أمجد، أمير، جعفر، سجاد، باسم، هيدر. بعد ماكو حد غير هسه رفعوا تقريبا 5 رافعين ايديهم للجواب، فبعد شباب نريد اكثر. هسه احنا الحضور تقريبا 38 شخص. السؤال مالتي ليه اذا ما موجود سكرابر شنو اللي يصير يعني؟ اوكي زاد العدد، صارنا 7 8. بعد شباب 38 شخص، قول 37 شخص اذا اخر استاذ عدي. بعد منو؟ استاذ مصطفى، تفضل استاذ مصطفى فاضل اذا تسمعني، تفضل استاذ مصطفى.
السلام عليكم.
السلام ورحمه الله على استاذ.
الله يحفظك استاذنا. استاذنا الفائده من السكرابر هو انا حتى انتفع بالاساس اللي هو الاشتوى.
صوتك راح شوي بعيد، ما دا سمعك. تفضل استاذ مصطفى.
واضح حتى تخلص من الغازات الحامضيه. انا عندي من اي هو يعني المين هو الاشتوى.
زين اذا ما تخلصت شنو اللي يصير يعني؟
هو هذا
راح صوت ما دا سمع.
مصطفى صوتك ليه جاي يروح على كيفك بس.
ما اعرف النت كلش ضعيف.
ايه
هو هذا غاز.
سؤال استاذ احمد يقول اذا ماكو سكرابر يعني ماكو سكرابر ظل ايش راح يصير؟
يسوي لي مشاكل بالتاكل يعني. اهم شيء هو انه تخلص من الماده اللي يسبب لي التآكل.
زين، غير التآكل.
غير التآكل شو يأثر على الكاتاليست؟
نعم؟
يأثر على الكاتاليست ولا لا؟
بالطبع يأثر.
اي بعد روح فوت. عوف التآكل هسه انسى التآكل بالموضوع.
نعم.
زين. اوكي، يعني انت جوابك قريب يعني، بس مو كامل جوابك، فخلينا نشوف استاذ كرار عباس، تفضل.
السلام عليكم استاذ.
تفضل. السلام عليكم. من بده يحكي؟ استاذ كرار عباس، تسمعني؟ اعطيني الجواب مالتك.
استاذ لا ما موجود السكربر، فالاتش 2 اس راح يبقى يرجع للرياكتر فيسوي بويزنينج للكاتاليست.
زين، وبعدين شو يصير؟
فراح تقلل الاكتيفيتي مال الكاتاليست.
زين.
ولذلك تسبب لنا يعني مشاكل، وكذلك مشاكل تآكل.
النتيجة شنو؟ النتيجة شنو بالبرودكت؟ شو يصير؟
البرودكت يطلع لنا يعني دي اكتيفيشن، يعني الافشنسي
لا هسه انت حكيت على الكاتاليست، دا اسالك البرودكت السائل شو يصير به؟
البرودكت راح يخرج وياه همتين، يعني الاتش 2 اس ام راح يخرج،
يعني ما راح يبقى 100 150.
فايش قد راح
نعم الكبريت راح يزيد، احنا نريده 150 بي بي ام.
ماشي،
بهاي الحاله راح يزيد.
بالضبط هذا رد اعرف. شكرا اساتذه، شكرا جزيلا. Thanks Pilar for waiting. I just want to
No, that's good.
the attendees. Yeah, thanks. You carry on here.
Okay, so now we will see more or less some of the operating conditions. Okay, this is for case 1 for BASRAF crude oil for the startup run conditions. Remember that we saw the other day that we have two cases, and in this case we are talking about the start-off run conditions, and we will have another PFD with end-of run conditions. So if we see here the reactors, okay, we can see here the inlet to the charge heater. This is the temperature, okay, that is a 319 degrees C. Then you heat it up to 339 degrees C.
Sorry, Pilar, just the voice is a bit low.
Okay. So here we have the feed, okay, that it goes to the charge heater. Remember that here we have both the VGO and the recycled gas. And then you go to the charge heater that is with fuel gas, operated with fuel gas. And then you will have here a temperature of 339 degrees. So you control the temperature of the reactor operating on the fuel gas to this charge heater, to this furnace at the inlet of the reactor. Here you have the pressure. You see here that we operate at high pressure at 114 kilograms per square centimeter. Then you have here the reactor 1. Remember that we said that we have 3 beds. You see it clearly, 3 beds. And you will have here a lot of temperatures indicators. Okay, a lot of temperatures indicators across the bed, in the bed, every point here in the reactor. Here, this in the lateral, if you see it, after bed 1, you see another arrow entering in the reactor. This is a quench. And as you can see, this is a valve, a control valve, and it is a temperature control valve. You can see here a TC we saw in the other online session about PFD. It's a temperature controller that goes to this valve, opening or closing this quench valve to this outlet of the first bed. Then you have the second bed, the same, you have another quench, okay? You have also, of course, pressure drop indications about the bed to see the activity and if you have some fouling in the catalyst. Here you see the reactor outlet temperature, the first reactor outlet temperature, And the pressure, of course, we have a delta P across the reactor, about 6 kilograms per square centimeters. And then we go to the second reactor, okay? Here, again, we start more or less at 36 degrees. And again, we have the 3 beds. Remember that we have here a little bit more catalyst in this second reactor than in the first reactor. And the same, we have here the temperature indications. And this is the outlet pressure and the outlet temperature, okay? And these are the other process variables that we mentioned during the presentation today. That is the operating conditions that they suggest for the unit, the pressure, and this is the liquid hourly space velocity, okay? For both cases is the same. You have a little bit of increase of the gas to oil ratio when you operate with the mixed-reef crude oil. You can do the calculation very easily with the amount of catalyst that you have and the fresh feed. And here with this gas that is circulation divided by the fresh feed. Okay, these are more or less the conditions of the operating So let me see if I have this. Now you can see the PFDs. Okay, you have a lot of PFDs for the unit. Let's see the complete PFD that we have seen. This is the complete for the reactors. Okay. At the bottom, as we have seen the other day when we saw the PFD session, you have the main streams summary here, okay? So these are the main process conditions of the reaction section. Here you have the duty of this charge heater, and here you will see that both streams, that is the feed, that is the stream 224, and the recycled gas, that is the 376, okay? And they mix here before the furnace, okay? And goes through the reactor and goes to all the other sections of the unit. So that's what I wanted to share with you today. So this is quite important, this unit, because it is the first unit for the vacuum gas oil processing. It is important to treat the vacuum gas oil before it goes to the fluid catalytic cracking that we will see next session, in order to meet the gasoline specifications. We have seen also that we are working with 3 beds in each reactor due to the reason that we have explained. We have a H2S, a lot of F2S formation, because we have a quite high amount of sulfur in the feed. That's why we have also to be very careful with the recycled gas purity to get an appropriate activity of the catalyst. So that's everything that I had for today, but if you have questions, please.
Thanks بلال.
Yes.
شباب أحد عنده سؤال؟ خلينا نبدي. أستاذ مصطفى فاضل، عندك سؤال؟ لو هاي قديمة رفعت الإيد الصور ما أعرف.
اكو استاذ.
تفضل استاذ حيدر الباشي الصور. تفضل استاذ حيدر.
السلام عليكم أستاذ.
السلام.
أستاذ راح أسأل سؤالي بالإنجليزي.
إيه براحتك مباشر اسألها. أوكي.
تمام. We have talked about H2S that is allowed to accumulate in the recycled gas, but what about the light hydrocarbons? Because we know that both of them can go back with the recycled hydrogen. So if can it goes high enough to disturb the oil to gas ratio? Can the amount of light hydrocarbons go high enough to disturb the hydrogen to hydrocarbon ratio?
No, because also we have this as two separators in the process flow diagram. In the first separator, it mainly goes hydrogen, and in the second will be the lighter components that will be separated from the recycled gas. So it is.
I think if you show the PFD, maybe it will become easier to
yes
understand. Yeah.
So if we see this.
Yeah.
So here you have mainly hydrogen with H2S, okay?
Mm-hmm.
And in the other, you will have this of gas that will goes here that will have the lighter components, okay? But mainly, of course, you will have also some light components here, so of course.
There is no monitor.
No pointer.
No pointer. I'm sorry.
Oh, no pointer.
Yeah. I think because you need to full screen. I think the slide, because now it's just PowerPoint file. Yes, now it's moving. Yeah, now it's moving.
Okay, so this is this where you goes to the. You
no
will
pointer
have.
Again.
Oh, well, I don't know what is happening now.
Yeah, I think if you do full screen.
Now?
Full screen, it will be easier, Pilar. If you go to full screen.
Oh, because I haven't what I'm sharing. let me see. Good. So here, that is this the recycled gas. You will have mainly hydrogen and some light gas, of course, but the other, the C1, C2, will go through this, okay? Because you will need to cool more the recycle to get this of gas. So in this, you will have, of course, some C1 and C2, but it will be a small amount and in the recycled gas.
Okay. So my second question is about the unit in general. Well, we all know that it is a hydrogen consuming unit. That's right.
Yes.
Okay. So and we've seen that in the formulas and the reaction equations. So but on slide 12.
Yes.
We can notice that one of the products is high purity H2 to polynaphtha unit. How can that be possible?
Yes, this is because this hydrogen here needs to be compressed. Okay, you need a pressure here because you have seen that we have very high pressures in the reactor. Okay, so this is like it goes through the unit. It is compressed. Part it is consumed in the HDT, and part goes to the high purity. Okay, to the polynaphtha. It is not produced by the HDT, but it was only to show you that this purity hydrogen goes to the HDT and to the polynaphtha unit, okay? But
in which stream it leaves the unit?
Sorry?
In which stream the high purity hydrogen leaves the unit?
It goes to the network. Goes to the hydrogen network refinery.
Maybe we can let me see if I come back to the Okay, to this charge. Okay. So let's, I don't remember which is the, you are seeing now the PFD, no?
Yeah, yeah.
Yes.
Here we have the makeup hydrogen, okay, from unit, from the PSA unit, and you go to these compressors, okay. You have one operating and one spare. You go to the first stage, you cool it, and you go here, normally no flow, and you go to the second part, to the second stage of the compressor, and here after this, that's, well, you can maybe see it later, but here after this you have another a part of this stream going to the polynaphtha unit. So what I wanted to tell you that is this hydrogen makeup gas comes here, it gets compressed, and part of this hydrogen will go to the polynaphtha unit. Here, okay, I didn't.
Yeah.
Okay. So it is only entering, being compressed, and goes to the polynaphtha unit, that is unit 9, okay?
Okay.
So
but it was only to show that it is not produced by the, it is not produced by the unit, okay? But it's compressed by the unit and sent to the other unit, to the polynaphtha unit.
Actually, it's compressed by only the first stage of
you use the compressor, yeah, and this
yes,
unit, and then you leave the unit, and that's it. It's nothing to do.
and leaves the unit, okay? It is
So we can say
only
it has
to take advantage of this compressor to compress this in the unit, okay? It is only compressed in the unit.
Okay, very good. Okay, that's all for now. Thank you so much.
No, thanks to you for your questions.
أستاذ أمير تفضل.
نعم أستاذ أحمد. Yes, sir. My question is there any possibility to make a regeneration for the reactor, for the catalyst? And what's kind of the temporary and permanent poisoning for that catalyst?
Yes, they always talk about possibilities of making regeneration in situ, but they don't recommend to make it because it is a very delicate procedure that it requires you can have very high temperatures, regenerating also the catalyst, and they recommend or to unload and send it to another company to make the regeneration, or of course to reload the with fresh catalyst.
So it's possible to make regeneration for that catalyst, not like isomerization catalyst. It's not possible to make any regeneration.
No, it is possible, but you have to take a very appropriate procedure. No? But they recommend to make it not in the reactor itself, but you unload it and you can send a specialized company to make the regeneration. I don't know if Ahmed, if you have had this experience of the regeneration in situ.
You are absolutely right. Yeah, so it depends. Yeah, whether it depends on the decision will be taken by MRC later on, whether
Yes.
you're going to hire external and comes to the refinery and does the regeneration, or you ship the catalyst back to the vendor and they do it and send it. But the method or the methodology of doing the regeneration is not being decided yet. But obviously, you have to follow the licensor recommendation and the catalyst vendor recommendation. So I think there is some of the catalysts, the vendor in Bahrain. So you have to send it to Bahrain and they do regeneration.
You have it, relatively close, no?
Yeah.
Okay.
Okay.
Okay, thank you. Okay.
Thank you.
Any more questions شباب؟
استاذ احمد برز احنا.
سلام جديد تفضل.
استاذ الضغط والحراره علاقه طرديه، فليش بالفلوينت مال الرياكترات نشوف اكو انخفاض بالضغط وارتفاع بالحراره؟
مو قلنا اكسوثيرميك غير؟ لو تقصد شنو؟
هو
التفاعل يعني نوعه اكسوثيرميك، فشي يسوي؟ يرفع الحراره.
صحيح، بس يعني ما يرتفع ويا الضغط او لا؟
الضغط ينخفض لانه عندنا طبقات.
مو انت ذاك دا تحكي عنه، المفهوم مالتك دا تحكي ذا بس فيبر، هذا ذاك الفيبر كلامك صحيح، بس انت عندك ديستريبيوترز، عندك الكاتاليست، هذه كلها تسبب بريشر دروب للسائل دا احكي.
اوكي استاذ. وبعد السؤال، ليش نستخدم 2 رياكتر؟
يعني موجوده هي التفاصيل، انه انت تسوي دي ميتالينج، تسوي قسم منها، تسوي شو اسمه يعني تقلل الميتالز ماكو الكونتاميننتس بالفيد، وبعدين تطب للديسلفرايزيشن. يعني اكو عندك مثل خلينا نسميهم جاردز بالبدايه، وبعدين تطب للديسلفرايزيشن والدي نايتريفيكيشن وبقيه التفاعلات.
اوكي شكرا جزيلا.
هلا استاذ. شباب اذا ماكو اسئله، انا لحد هسه بعد ما شفت احد عنده سؤال اضافي، ان شاء الله يعني برخص الاستاذ عدي الخميس، مو هذا الخميس الجاي عندكم امتحان بالسي دي يو. Sorry Pilar, I think that's done for today, but I want to talk to the trainees for the test about for group A next.
Perfect.
Yeah, so thanks so much Pilar.
Thanks for your attention. Bye.
Yeah, thanks. اي شباب، فالموضوع ان شاء الله يعني على السي دي يو الماتيريال، الاسئله راح تجي من الباوربوينت، المحاضره مال البي ام سي،